right, you guys can see this okay, right?
Yeah, looks great.
Okay, so I guess a couple of things. First of all, does everybody agree? I think there's no disagreement on the fact that the real main hall transponder we would use is probably going to be both digital in both uplink and downlink.
Correct.
Do I have to make a case for that, or is that under
No,
kind of like?
No, not to me, and not to anybody that's actually plugging away on making circuits
You know,
code.
there would have been a time where this would have been heretical within the amateur community, that's for sure.
Oh,
But
yeah, I fought through that in 2017, 2018. It's yeah,
yeah,
but no, I'm
okay, so
solidly in the all digital up, digital down. It regenerates, it multiplexes, that's what it does.
yeah. Okay, so if you buy into the fact that we pretty much have to talk about higher orbits for operational systems, yeah, LEOs can work, but even LEOs might want to be digital. But for an operational system, the way to get the capacity up is to take advantage of the gain that you can derive. And of course, at the same time that we're going up in altitude on an operational sense, we're also going down in spacecraft size because of cost. You know, we aren't the first guys on the block to ever launch a little spacecraft anymore. There was once when I could stand on the top of the gantry and say, my God, this is just amazing. We're launching our own spacecraft and it's little and it really works. But I can't say that that's a unique thought anymore. But in 1974, when AO7 was launched, and I was really proud, those days are pretty far gone. So anyway, and as we go up, of course, the way to win the game is if you have gain on the uplink and the downlink. The higher the frequency, the more capacity you can have. Because you're canceling one over R squared loss factor that you would otherwise have. And the other aspect is that if you're using digital and you use forward error correction, by going to the double coder decoder world, like you get with DVB-S2 or S2X, then you're getting the required EBNO, signal to noise ratio, C over N0, whatever you want to call that parameter, which is signal to noise ratio. You require way less signal to noise ratio by about as much as 16 to 18 dB than you require if you don't use any coding at all. So the win is going up in frequency and up in FEC coding level. So is that concept okay?
Well, that's what they gave me a master's degree about, so I'm with you so far.
All right, very good. All right, so now to the spreadsheet. This is an evolution of a lot of different things plugged together and a whole bunch of new stuff added in. But I've never actually used it in a corporate environment where people actually use this thing in a configuration and control environment. But I set it up to be able to do that, so that if you have various engineers and overviewers, project managers, or whatever, if they tick the box, then their box turns green. And when finally there's some configuration control dude who says, okay, we'll do it, then the whole thing turns green. Now, the idea is to passcode protect these green squares so that you could only enter it in if you are the comm engineer, if you are the PM, and so forth. And so once all the boxes are green, that means the document's ready to release. So that's just a toy I put in there, and I put all kind of notes to try and make it easier to do document configuration control here.
Cool.
So that was what the first page is about. And then the second page follows up. Every time you do a revision, this is what the revision tree looks like for this document. So it's been revised, and you see it goes all the way back to August of 2010. And some elements of this actually go back to about 2001. So this is long in evolution. And what I try and do is use colors in a specific way. And I do this on every single spreadsheet I do on any subject, is I make the blue cells the entry data, the yellow cells the results. And if they're black or blue means I can probably change it without stepping on the formula. Black, if I modify a cell, it's just a white cell with black text, I'd kill the formula, and I might as well start over, because the spreadsheet probably won't work after that, or I won't be able to change some parameter at all once I've screwed that up. So it's always a good idea with my spreadsheets, since I haven't password protected everything in them, to save a clean copy of it. So you always have a fresh copy in case you step on cells, which I do to myself all the time. So that's it. Oh, I see something I forgot to do. Up here at the top, it says enable content. This has to do with the way this software uses the rain model. Remember, the rain model uses
yes.
Yeah, what is it?
You mean the standard, the
No,
database, the database?
Yeah, it uses a database, but it also modifies, oh gosh darn it, I always do this to myself.
CGITC model?
It's an ITU model.
Yeah.
But, it uses macros. So this enables the macros to be used. So if I enable that, let me see if I can show you here anything. Let's see, look at the downlink here. No, it's still a valid copy, so it's not going to prove that I'm doing it.
Yeah, we ran into this before, because it looked like a valid copy on my Macintosh, and you said that's impossible.
Yeah, right up until you change one of the critical cells, it will work.
Yeah, because you had me.
So the as delivered copy works, and then after you make one modification, it won't work anymore.
Right.
So
that's exactly what happened.
Yeah. So if you've done this properly, you should get this inquiry here, where it asks you, have you just enabled or disabled the macros, and so you enable the content, and so then now we have made it so that the ITU rain model will work in this Excel spreadsheet, and we got to still solve that problem for everybody. It turns out for the fix I gave you works for older versions of Windows 10, but not after about Windows 10.4. I think you and I discussed this, but there was an epic beyond which, if you've got a newer piece of software, then it will not recognize 32-bit words explicitly. You have to tell it some piece of information we haven't figured out yet, so it knows this is a 32-bit piece of software, not a 64-bit piece of software.
Exciting.
And that's where we're hung up right now on that. This machine is an old machine. It uses an old version of Windows 10. And so when I put that DLL file into my System 32 folder, it does it and it works properly. Okay, so the way you drive this thing is I've put in what's called a scenario planner, which allows you to make quick changes to things you want to find out. And these are all the things in the blue area here. I've got two methods of changing the antenna size. One is changed on another sheet I'll show you, or I can alternatively use another antenna here. So I have two ways of defining antennas. Specifically on the user terminal setup, I do it. And it's done there, and the other way is to do it here. And the upper one assumes that the antenna size for the uplink and the downlink antenna could be different, which could easily happen in the amateur service. Whereas if you have the common antenna for up and down, it assumes you might have a diplexer or something in 2 different feeds on the dish. So it depends on which one you'd use there. I select the receiver bandwidth, but the way I've got it set right now, it's kind of from some old commercial stuff. It gives you an option of what ones you can pick. And if you don't like that, you have to go over to this section over here on the right and load in different options. And that's kind of clunky right now. So that's one thing I don't like. And then, so I've got it set now so I have the receiver bandwidth is very narrow and the transmit bandwidth is as wide as it can be. Now, that means we're kind of operating the downlink as a combination of all the uplinks. So think of the downlink as a TDMA and the uplink as an FDMA, but it could be an FDMA, CDMA type of link. But right now, I would say this is just until this was socialized so we could figure out what we really wanted to do. But this assumes 10 kilohertz channels. And at these microwave frequencies, that's pretty narrow to try and keep track of. And Phil Karn had lots of ideas about how we could get around he didn't mind the narrow channels, and he felt the receiver could be smart enough to keep track of a whole bunch of channels at the same time, even including Doppler, and even including the fact that the user may have a pretty lousy uplink stability oscillator, and it could be able to do that. So that needs some more discussion than we have time for today. But I've assumed here that we have a very narrowband uplinking user, and there are multiple users. So this is an FDMA multi-access thing, whereas on the downlink, we're assuming every user is receiving the same carrier with the same modulation and the same coding and the same mod cod step. And so the channel sorting out is done in TDMA in that mode. So that's the assumption made here. We're only looking at one channel on the uplink and one channel on the downlink.
Right.
And for the rain, we've turned off the rain, which really turns off the cloud attenuation and the rain attenuation in the ITU link model, not the rest of the losses like the atmospheric losses, which are very critical as well. So I have what you call the clear sky condition and the rain on condition. So we have the rain. It's asking, is the rain turned on? The answer is no. So that's the clear sky. But if the rain is turned on, the statistics it applies are 99.5%, which means the rain is such that 99.5% of the time this link will work, and 0.5% of the time it will not. Statistically speaking, so that amount of rain is what is computed by the rain model.
Okay.
And then the last point here is that if I have a green parameter, it means it's transferred from another page, and we're going to talk about the earth stations in a minute. But you'll know that for anything that involves a lot of rain, like 24 gigahertz does, that you will the link will very much depend on where you're located. So I made it easy to be able to swap link user locations. So you could just plunk the user in. It will flow into this sheet and then into the rain model, and it will instantaneously change the link for that location, latitude, longitude, and altitude. So that's how this parameter is used. It's passed on. It's just to let you know at a glance, this link is for this location.
Right.
Right. Okay. Now, and then what it does is it tells you the results here. So I put in those gross parameters. There's obviously lots of other parameters you want to know, but if you want to play with these parameters, you can do that and see immediately what's changed. So the first is for an adaptive mod cod, and I've assumed here will not be able, and there's a long discussion we could have about the DVB-S2 mode. There's VCM, ACM, and CCM. CCM means I'm never going to change the mod cod step. VCM means I'm controlling it by command. So the command operator actually has to enter in to the decision on what mod cod step to use. and ACM is adaptive coding and modulation, where the link is conditioned by what the user's uplink is. The downlink will be correspondingly adjusted, or vice versa.
Yeah, we are,
So
our baseline is ACM, and that is, we've also worked in adaptive coding and modulation has worked into the authentication and authorization and the startup and the acquisition. So our baseline is
so
ACM.
it would make it therefore more difficult to determine based on power available how many channels were available and how you know what the channel loading status is.
Yes.
But just for the sake of this discussion, I'm using VCM here, which means the telecommand operator is keeping track of what the status of the loading of the transponder is, and it changes the mod code step when, on average, for all the users over the whole earth that are looking at this transponder and using this transponder, what the average performance for those users are, because some users are at low elevation angles, some are at high elevation angles, and the difference in the performance, given how dynamic DVB-S2X is, you can have a very big range of settings you could use here. And they would work for some users very well, but they'd work very poorly for other users. So not sure, that's a whole discussion area, but what this is the results of the uplink. So what this is doing is summarizing the whole situation for the user uplink. It's the bandwidth, what mod code step was satisfied, what the data rate was. So in a 10 kilohertz channel here, I got 16.9 kilobits per second. I have a spectral efficiency of 1.8 bits per hertz, or bits per symbol. It's giving you some feeling for what the 99.5 link range situation would be.
Hold on for a minute. Hold on for a second.
Sure.
Our uplinks are totally independent from our downlinks.
Exactly, here.
And
yeah, they are here too.
Our uplinks will not be DVB2 S2. They'll be a more conventional modulation.
Okay, well, I've assumed here that they're
coded. They'll be coded.
Yeah.
You know, there'll be something you could use as an approximation, one of the CCP, you know, models, 1/4 to 3/4.
Right.
Okay. Well, but okay. So I'm not. And can the user change their FEC coding from different steps depending on his conditions?
No, it's all automatic. He'll basically his
Well, I don't mean the operator necessarily, but does the transmitter itself adjust to the link? So there are different forward error correction values.
Yes, the receivers as part of a startup transmission will determine what frequency is actually being used. We'll lock to that frequency, and we'll adjust the input filters to get the maximum performance.
Okay, so but you're not using the coding schemes as specified in DVB-S2.
No, not at all.
Yeah, you can see here. Sorry, go ahead.
Oh, it's okay. I can send you the protocol for the uplink because we now have one, and I'll make sure that you get a copy. It's pretty cool. Yeah.
Well, okay. What it would do is it would change the table I'm going to show you here that selects this, but as long as there are multiple steps, then what would be displayed here once adjusted would be what was achieved in the link result. So it says, okay, this is what I was able to achieve for the price of this parameter right here. This data uplink carrier to noise power density ratio. Think of this number, if you will, and it's used in almost everybody's digital communication link parameter set. It's the equivalent of the 1 hertz bandwidth signal to noise ratio. So if I put a carrier of this strength into through a 1 hertz filter, that's the signal to noise ratio I get out of that filter. So it's an easy way of, and it's a nice number that goes from, the low 20s to above 100, and it gives you an indication of link performance. It's nice in the way of you mentally thinking about it, but in addition to that, you always know that's the signal to noise ratio I get if I was putting that whole signal into a single carrier and I was looking at it with a 1 hertz filter on the ground. And then it tells me, oh, by the way, you've got clear sky conditions, atmosphere and scintillation only are the only 2 excess path loss factors considered. This is the achieved signal to noise ratio. And if you want to talk about energy per symbol to noise power density ratio, which is another thing used as a common parameter within the DVB-S2 world, that's that computed version of the signal to noise ratio. Then you have the same thing for the downlink, but here you see the bandwidth is now up to a megahertz. And in a megahertz, I can actually get through that thing at I think I'm using a Nyquist roll-off, which is how steep the skirts on the filter are. I think I'm using 10%. I might be using 5. I think I'm using 10%. So yeah, it would be 10%. So I can get.
It doesn't go that low. It should be, I believe the lowest is 20. We'll most likely
Megahertz.
use 35.
Well,
But
megahertz,
we may understand that we may not have we'll have a filter. However, there will be spectral growth from clipping that might occur in the output stage.
Spectrum regrowth, yeah. I've got ways of adjusting for that, by the way, in the model here, but that's down in the guts. But this is the net effect of what you remember. What we said, the uplink is separated from the downlink. So the uplink, the guy who, when he's either talking or sending digital text or video or whatever he's sending, it's going to be digitized and put into a payload computer. And then that payload computer is going to insert the results of that whole guy's uplink data stream. He's going to merge it with the other uplink data streams into a TDM downlink stream. That's the assumption I'm making here.
Yeah, well, the multiplexer is essentially, it is doing some processing of the data to eliminate some things that aren't necessary and handle call signs and things.
Sure,
like that.
sure.
You
yeah,
can
and it might even, I could imagine it would even realize maybe you need a parameter that says, this is a voice conversation, this is special data, this is video, It might have modes in it or something like that.
Yeah.
I realize there's going to be all kinds of cool GUIs and things going on for people to know what they're getting from the other guy. That's understood. But this is just, if we're looking at gross bits here in the data stream, and what it's saying is, okay, for this case, and we'll show you where we are. I think we're at apogee in this right at this minute. I can support with DVB-S2, it will support QPSK rate 1/2, which is about the 3rd modcode step in the DVB-S2X stack. And I'm getting, for that 910 megasymbols, I'm getting about 0.9 megabits per second out of the link. And the C/N0 that gave me that was 60.62. And my spectral efficiency, which is kind of something I like to keep track of, is about 0.98. So right about a bit per symbol. And then the rest, and you can see the C/N, or the signal to noise ratio for this link, is only a 0.5 dB. Now, there were days when NASA couldn't decode a link like that. I mean, that's a pretty shabby signal to noise ratio. And the fact that we can get, almost a megabit per second out of that kind of signal to noise ratio shows the power of DVB. It's really cool. Okay, now I put this new thing in here because it's a discussion area. If you assume that every bit that goes up, give or take some control bits, is going to have to come back down, then the downlink capacity, my metric here has been that with a 6U spacecraft, I wanted to be able to tell the commission that we could support a minimum of 100 voice grade communications conversations, which means 200 users minimum could be supported with this asset. So if I use 6.25 kilobits per second as the threshold for the data rate that must be closed by the average user, then I can have an average channel count on the downlink based on the fact that I could get 899 kilobits per second. If I had to divide that into 6.25 kilobit chunks, I could support 143 channels. However, the link on the uplink supports 16.95 kilobits for this particular user. So is that confusing in any way?
No, but in the way
Michelle?
that,
I don't think it's confusing. I think our baseline assumption is to have a much wider channels per user.
yeah, see,
Well,
anyway,
all right,
back to Wally.
So what we're going to talk about now is what happens when various things happen. But what I can tell you is I'm wringing the wash rag about as hard as I can for the power I've got available at the frequencies involved and for the locations on the earth where I have. I've got quite a. This is about as far as I can go. So okay, so let's just continue. But I put this summary down here, and the main thing is to see, regardless of where I am in the orbit and the kind of users I use, I'm always checking back this parameter here. And this is just a figure of merit for me. It says, I want that number to be very close to 100. And if I do that, then I, as an operator of a satellite system of this kind, am meeting my commitments to the community to provide this 100 channels for two-way to N-way communications.
Yeah, I strongly concur with having that always be something that we can either generate or derive.
Yeah, and how you do that is going to be involve some very fun, cool software, I think, in the system. Or you may have a different way you configure the whole thing in mind that I haven't come up with yet, which is entirely possible. But this is the way I wanted you to understand the way my brain was working on this. So if you're trying to optimize this, what you're trying to do really, I think, is first try and get the downlink down here in the bottom. We can go back, we can go to the downlink here. This number here, we want to try and optimize that number because that's going to, I found it sets my capacity a lot more than if I try and optimize the uplink number.
Right.
Because that this causes the channel count to cap more than the uplink does.
Right.
Which is an interesting finding. I mean, you have to actually run enough of these to come to that conclusion. That is the conclusion I've come to.
It's not. This is really exciting to see and really useful. Because I don't know if we have talked about that or have had an appreciation for that type of uplink downlink interaction yet. At least I'm speaking for myself, I haven't. Wally probably has, since he's done this class of work in the past and is. But yeah, having this in the spreadsheet and being able to check it when you're walking through is really valuable.
Yeah. So we could talk, now you can think about this as a data rate, but imagine this is after all the coding has been stripped off. This is the true bits, I think what you call raw bits delivered to the user. Now that in this particular example, the user is actually able to achieve 16.95. But why did I not use a higher number here? The reason is because if these are the raw bits and these actually get presented to the computer, which is going to do, let's say just packs those 6.25 kilobits of data into the downlink frame, and the downlink frame is sent, and the user, the ultimate user on the end, is going to receive those 6.25 kilobits from the other side of the link, from the guy he's talking to. All right, now he's going to put that into, if it's a talking to, since he's not using single sideband, he's going to be using a vocoder, right? He's going to be using a voice decoder here. Now, the real question is, what do you need in the amateur radio community to make the average ham happy about the data he's listening to as a voice? Now, if I go to commercial standards, you both probably are familiar with good old Iridium.
Yes.
Who decided that the vocoder they would use in their satellite phones was going to be 2.4 kilobits per second.
Right.
And then you'll probably know that Globalstar, which was designed by Qualcomm, the data standard was designed by Qualcomm. Qualcomm uses a voice decoder after the removal of some overhead bits. They go into the vocoder at 8 kilobits per second.
Right.
Now, the Iridium one sounds like crap, and the Globalstar one sounds like stereo, stereo coming over your car radio. All right, so I would say that the Globalstar was too good, and the Iridium was too bad. So 8 kilobits is too high and 2.4 kilobits is too low. So I figured an amateur might be okay with 5 to 7 kilobits per second. Now that's how I came up with picking that channel.
Yeah, I think
way too high.
Wally's pretty happy, I think, with the numbers that you're talking about. To me, I'm very much one of the absolute requirements is this: we cannot have crappy voice, we cannot have crappy codecs. The quality has to be really, really good, and that's
but
just
understand, Michelle, there's two cases. There's one, what we actually do on a day-to-day basis, and number two is how we demonstrate our good shepherdship, that we're good shepherds of spectrum.
Yeah, I don't think it's wasted to make it sound gorgeous. That's not squandering spectrum or anything like that. We don't have the same motivations as the commercial people do for squeezing lots and lots of subscribers out of every hertz.
I think the fact that we're having this discussion would tickle a member of the Federal Communication Commission to think that we actually are thinking about this trade factor, that we don't want to present crap to our users.
That's right.
And we want to be good shepherds of our spectrum. So we're struggling with this number. So what I would tell you guys is this number to me, along with the channel count, they set the way the real transponder system works.
Yes.
If there is only one kind of channel. Now, you guys could tell me, well, I could break this transponder up into multiple transponders, each with its own data stream set, so that maybe rather than having one TDMA link, I have 2 or 3 TDM links. One is for voice, one is for data, and the other is for some kind of video link.
Correct.
Slow scan.
You can.
Yes,
that's
totally
a good summary of this. They're independent, and we are not going to build in a codec. That's a application layer.
No, I assume you wouldn't build in a codec, but this still is what that 6.252 is telling me is that's the average data rate that I want to achieve for the average user, regardless of elevation, angle, and location, and that number will ultimately, along with the downlink performance, that 898.96 kilobits per second, that will tell me how many channels I have available given the ERP I have from the transponder.
Right. Totally
Right.
on board.
So that
Just
when I
for
give
case-
you guys when I give you guys this adjusted spreadsheet, taking into account whatever changes we make because of, say, you're not using DVB on the uplink, then you guys can, along with the user community and people who are helping, you can socialize this and figure out what everybody wants that number to be. But it's one of the key parameters. This box contains the key parameters for the system.
Yeah, if somebody wants to sound like ASUS System Fusion, or if they want to sound like Iridium, they can choose the application that provides that. If they want to sound gorgeous, you know, and you're going to be able to recognize the person, hear the emotion in their voice, that sort of thing,
but
then that is a different application at the user level.
But be aware, if they end up choosing a larger number for that blue box, then they are using more spacecraft resources, which
That's
make
right.
less space. So this becomes a socialism.
Yes, you're right. It does.
Debate.
Well, in practical terms, our channels are 800 n times 800. And they range from 800 to 1200.
Channels in the transponder.
Yes, as we pass them over from the multiplexer as they're passed over, any channel can be allocated n 800 bits per second.
Yeah. Okay. So what you're doing is you're channelizing the bits, whereas what I'm doing is letting the bits change, and I'm trying to express that as a channel count. So I'm using as a variable the channel count. You're keeping the channel count constant and adjusting other parameters to make that work. So that's
yeah, I think
exactly.
both are valuable, and we need to make sure that we understand both our assumptions and then this really useful way of looking at it, you know, because this speaks directly to a whole lot of architecture.
Well, this is a complicated thing we're doing here. So
that's right.
I'm just showing you my slice at it in the way it evolved. It evolves in the case of this, in the expression of this link budget, because of all the prior experiences I've had with both amateur and commercial communications and everything else. It's a synthesis of everything that's happened in my career. So it's not so surprising that, you know, I have a particular flavor here, but because it's such a sophisticated standard, we could do this many other ways. So that's what I'm trying to do, is get to yes here if we can figure out how to do it.
Right. Yeah, we've got so there's many directions and ways to do it. It's very exciting.
Yes, in practical terms, what a station, how many bits a station can uplink will be based on that station's performance, mostly antenna size and power.
Right. Well, and that's okay for that. Okay. All right. Let me think about that for a minute. And so we aren't here till midnight tonight, my time. We probably should kind of move on here. What I've got here is, now we're going to talk a little bit about the orbit and how the orbit figures into this whole thing, along with antennas and stuff. So this comes from many of my old spreadsheets. This is just a mini orbit summarizer here, which actually works if you're just thinking about orbits. It actually dynamically computes some things, and maybe you don't need them all here. But the key point is you want to set the in my blue boxes, you want to set the apogee height, and that's the height of a geo orbit, 35,786. And then the height of the perigee, let's talk about that for a second. We go back to the Iridium and OneWeb and friends. And that is that these guys are going to say they own these altitudes. And the highest altitude I know that's been assigned is, I think, 1050-ish.
Yeah.
1050 to 1100. I think the highest one I really know of for sure is 1100.
Yeah, previously, and when we've talked about this before, I think we decided to give that number a little margin.
Yep. That's why I came up with the 12. We came up with a 1250.
Yeah,
but
I think it's a good
and
number.
You'll see that reflected in that delta V calculation document, which I also gave you. So anyway, if we do 1250, it means we fly over the heads of all those other constellations which are down here buzzing around the Earth. So we're a little bit above those. So even our perigee doesn't cross through the orbits of all this god-awful NGSO FSS mayhem nightmare that's going on that SpaceX is creating. Okay? And we go up to, we just kiss the geo altitude. I mean, you might make that a few kilometers less or something. So we technically never get into the geo world either. Depends on how you want to play this game. I can tell you that when you're launched into these orbits, there tends to be an apogee bias on them, so that rather than going to 35,786, they'll really put you at about 36,300. And since we'll be riding with some geo operator who's going to own that rocket, they're going to set the apogee, but realize they're probably going to set the apogee a little bit above the geo altitude. That helps them for some reason in their propellant management. I never exactly understood why the geos do that, but they do it all the time. So you might be in a starting orbit that's 36,300 or so by 250. So what we have to do is take it up from 220 to 250 up to this 1250, and that burn cost is about 100 meters per second. All right. So now what we do is we care about how we perform as we're at these various points along the orbit. So I just made a list here, and I called perigee 1 and apogee 13, and I put down here 14 for somebody who wants to put some in-between values. That's a user-defined parameter there. So at 14, I can go put in these parameters. I think actually, let me see if I change that. It does change 166. Yeah, it does. So I just have to change whatever the mean anomaly I want to look at is, and it will calculate the other stuff for me. And don't worry about this, but there's some subtleties about the amount of the Earth you see and what the noise temperature will be. I see if I've lost that value. That's supposed to be the noise temperature of the oh, that got erased. That's me stepping on myself. Okay. So anyway, what happens here is I can pick any spot I want around the orbit. Now, there's some parameters involved. This alpha value is what am I going to do with the bore side of the main antenna that I'm pointing this spacecraft with. In other words, I'm going to point, if this is a dual frequency antenna, I think you said, then the bore side of that antenna could be offset from the line of the instantaneous line between the center of the Earth and the center of the spacecraft. I could off point from that, but I've made the assumption here that value is 0, and you'll see it here expressed in this cell, which is K31. That cell allows me to offset the angle of that antenna. But what I'm assuming by putting that at 0 is that alpha is always 0, regardless of which case I pick between case 1 and case 13. So another way of saying it is I'm always nadir I'm always nadir looking with that antenna. So is that okay?
Well, what kind of station keeping is required to do that?
Normal station keeping that you would require for any LEO or any system that has an antenna with the gains of the kind we have here. And we can talk about that. But we assume that this is going to be 3-axis attitude controlled spacecraft.
Okay.
Now, all 6Us and bigger spacecraft that are launched right now for the rest of the community, all is pretty well standardized on using one of a couple kinds of wheels and star tracker. They use a star tracker. So we can point these 6U spacecraft to about 0.01 degrees sustainably.
Okay.
Now,
And that's
there is a problem.
You have
with,
to dump the wheels?
Yeah, that's the rest of my sentence. There is a problem with dumping the momentum from the wheels, and we had it in the old phase 3 program as well. We were controlling. We didn't have star trackers. We had sun and earth sensors, but we had the same requirement that we had to dump momentum from the wheels, or from the spacecraft at least, because it was a spinner spacecraft. So our wheel was the spacecraft itself. But be that as it may, we did have to remove momentum and dump it. And the only place we can do that is at the perigee of the orbit. That's another reason for setting that perigee as low as we dare. It also will reduce our delta V to raise and lower the system, but it also sets the amount of time we can effectively torque to remove to dump the momentum, angular momentum. Okay. Yeah. All right. So the rest of this in the yellow table here is describing where we are with respect to the antenna roll off and everything. And let's go to another. This is a summary chart to allow you to see how well you're doing and to set the two important. What you're doing on this page is setting two parameters. One is which step case am I going to use? In effect, how high up is the spacecraft? That's going to be important to the link budget so it knows the range it's got to communicate over. And it's telling you if I'm at step 13, I'm at 35,786 altitude. If I'm at step, let's pick another one, 9, then the range goes down to 13,399 kilometers. So that adjusts that one. The other thing is think about the users in this model by virtue of their elevation angle as the most important parameter. If I put in 10 degrees here, as I have, it means the locus of points all around the Earth in a ring of all those users that would be at 10 degrees elevation angle, give or take. Okay, so when I put in an elevation angle, think of not one user, but all the users that have that elevation angle, and this link would work for all of them. Okay.
Gotcha.
Yeah, and for 10 degrees elevation angle at that altitude, the slant range to that user at 10 degrees, all those users at 10 degrees, would be 45,586. Okay.
Now, do you have Doppler in here?
No, I do not put Doppler in here. I could put Doppler easy enough in this gray table here. If we put it, we'd have to decide whether we want to do. Well, we could put it both in uplink Doppler and downlink Doppler could be put in this table, and that would be the appropriate place to do that.
Okay.
Yeah, that's a good suggestion. So we know what that would be. Good point indeed. I tried on these yellow parameters to define a little more what I was really talking about here. But as you can see, by driving this, if I change these links over here, I can immediately tell what I've done to my C over N plus I zero. That's the end ultimate link result on the uplink and the downlink. I think I got that right. Yeah. That's the uplink. That's the downlink. Okay. And now what I'm trying to do is keep track of where in the heck.
In addition to Doppler, and it may be too complicated for the model, it would be useful to have the drift rate.
Oh, the drift rates are there. The omega dt is how much the argument of perigee changes, and
Right.
d omega dt is how much the right ascension changes, the orbit plane changes in
Yeah.
degrees per day.
Say again?
Okay, so those are in.
Okay.
And it's telling you also what the nominal period of the orbit. Here we go. I can't draw my own. There. Okay, now I got it. All right, so over here on the right, what we have is a pictogram of what's going on. You see that parameter up there at the top, alpha again. So that's how much I'm off pointing this thing. But it's telling you now where, with respect to the user, is this beam I'm going to place. So you can see that the zero elevation angle, which is the rho parameter here, is defined. So you can see how much of the Earth is illuminated by in degrees by that angle. You can tell what angle the user is at relative to the beam center. So the beam is going to be centered on this line. And then I don't recall anymore what my blue cone is. But anyway, again, I can see what uplink and downlink I've achieved is. And these are all, this is just an observation table. You don't change anything in this table because you'll see there's nothing that's blue. But the main thing is you can see for this user at 10 degrees elevation angle, how much downlink beam roll-off has occurred and how much uplink beam roll-off has occurred.
Now, do you have any allowance for the pointing error at the?
I have a pointing error in the real link budget, yes.
Okay.
It's not, it isn't quite so easily reflected here, and you'll see that. Okay, so we've done with with sort of, this is where you can visualize what's happening with the orbit, and particularly what's happening with respect to the beams. And the real thing to notice that's going to interact here is as I come away from apogee and start moving more toward perigee, my beam width is not likely going to change unless you guys are building an adaptive beam width antenna. That would be great. But the effect of having a fixed beam width as you get closer to the Earth is you're beginning to under illuminate the Earth. Therefore, users at lower elevation angles are going to be seeing more and more roll off from the beam that you're creating toward them, either on the uplink or the downlink. And you can see here from this one, in this case, the spacecraft's at apogee, the user is at 10 degrees, so he's off pretty far off the line of apsides, the semi-major axis of the major axis of the orbit. He's pretty far away from that, so he's going to see the worst case effects of the beam roll-off. He's going to be at the largest angle away from the bore side, and you can see for the downlink antenna, for its gain, he's rolled off 1 dB, and for the uplink, he's rolled off 3 dB. Okay. All right, we'll come back to this. But the next thing is I realized that because this is a rain model, that the location of the user is going to make a big, huge difference. So what I wanted to do was be able to plug into the case you're studying very quickly, a place where you can change the user. So right now we've got number 9 in there. So that's Boulder, Colorado. And that's an intentional choice because I consider it sort of the average rain loss location in the whole US. It's not a wet place and it's not a dry place. And it's a place where there are lots and lots and lots of meteorological measurements made because NOAA's there, NCAR is there. Everybody who knows anything about weather is in Boulder. So you can find out the weather conditions in Boulder better than any place on planet Earth. So that's why I use that as a reference location. So what this shows you is Boulder, the frequency is going to be used at Ka band and X band, that this is its location. This is the height above sea level, which isn't exactly right. 16. Yeah, it is. Yeah, that's right. That's right. So anyway, it then takes this value and plugs it into the Link Scenario Planner tab 3. And then immediately, when you change this value, the rain model will say, oh, you want the rain model for that location, and it produces that and stuffs it into the spreadsheet. Okay, so the whole point for this is I had some, here's like the workstations we use. Here's the spots for KSAT, if you know that, those guys. And these were just other random ones that came about. But you guys will want to fill in your own. And I've got up to 19 of them plugged in here. So once you plug these in, you can select 19. And it will give you the values for it. And of course, there's no data in it right now. But once you put the data in, that data will come up and it will be put into the system.
Oh, okay.
Okay. Right. That allows you to figure out the effects of rain between two locations.
That's really cool. So this is new.
Right. Yeah. This was new. This was done for the last commercial upgrade, but I realized it'd be extremely useful if you put all the places where the biggest users of the system were located. Like, you put W5 so-and-so here and so on until you've got a suitable list of places which include dry places and wet places and more. If you know where most of the users are, you want to put in more data points around those users, and then it will tell you the effects of rain. And trust me, that rain is a big deal here. It will affect these links, but it's part of the fun of playing this game. Like if you're working 20 meters, you really care about what the mean free path is and what frequency MUF, the max usable frequency, is. If you're working 20 meters, you care about that. If you're working 10 meters, it's even more important. So all of amateur radio with respect to propagation is a gameplay, and that is no different with millimeter wave. I think it's exciting because amateurs will learn so much about rain losses from what's going on here. So one of the benefits of amateur radio here is when you learn about new phenomena, and meteor scatter is a perfect example where hams were the best meteor scatter guys around. They could tell you more about meteorite propagation than any specialist in the entire world. So it's a place where we can shine. So I love the fact that the rain plays a game with you here.
Yeah,
and it allows
this is exciting because it's so often presented to us as just a negative.
Yeah, so we can sell that as saying it and compare it to like meteor propagation and how amateurs led that intellectual field during the time when meteor ionization was being investigated by physicists. It's the same kind of thing. It's where we can play in the game, and they put us on 24.05 gigahertz is right on a maximum rain loss line structure. It's a peak in the spectrum, and that's why they gave it to us, because nobody else wanted it. So I figure we might as well use it to advantage, and so this is kind of the reason I put this particular page in, is we can play games with that and see how This is actually what difference it makes, guys, if you do that. Okay, the next one's the standard gobbledygook. You got to put in the mean uplink frequency and the mean downlink frequency. And this just displays the bandwidths, the path losses. It's a summary to give you the elevation angles. Again, almost every data sheet, it gives the slant range, everything you need to know about the link. If you've got a bandwidth, it's also telling you the upper edge of the band and the lower edge of the band here. So if you modify the beam width in this channel, it gives you all the right numbers there. So it's just a handy spreadsheet thing to have there.
Yeah, very good.
All right. All right, now we get on to the serious stuff. This is how I set up the transponder. This is the page that sets up the transponder. I probably won't go into a lot of detail here, but again, remember, I only changed the blue values. So what I've got, and this you'll find, of course, not a big surprise, is one of the most critical parameters in the whole system is what is the maximum transmit power. Wally, to your discussion about intermod and things like that, I can set in the output back off that I use, and then depending on how much I back it off, the transmitter DC to RF power efficiency will change. So if I put 3 in here, this is going to drop down to like 20%, but the intermod will get better. So you have to know for your SSPA or HPA that you're using what the 1 dB compression output power is, how much you want to back it off. At that back off point, what is the efficiency? Because it's also going to tell you how much spacecraft power you need. On the final page, it tells you, okay, you need this many watts if you want to run the system this way.
Right.
And then you have to measure probably either the noise power ratio version of the intermod or the third order intermod products, whatever you want to do, and you can represent that there. But that's actually used in the final to actually subtract off the power that's creating the intermod from the useful power of the transmitter. So it's actually used in this system to offset the power that's wastefully used in producing intermod. All right, so it's telling you here, okay, so this system with those parameters, it's going to take you 35.7 watts to run that 10-watt transmitter. Okay, then over here it allows you can change, but these two parameters are adjusted on it, put in another page. This is put in the tab 3 link scenario planner, and this is also put in the link scenario planner. So this is just reflected here. I've got one channel, and that channel is 1 megahertz wide. I'm using it adaptively, which is a bit of a lie. This isn't used anywhere. It's just a helpful thing to you to tell you how you're actually adapting. It could be variable, adaptive, or constant, or fixed. Whatever you want to put in there, you can. But it also can be used for modulation. So if it's BPSK or QPSK, you can put that in there. And then if you have multiple channels, it will divide up the channels into the number of megahertz or kilohertz per channel, and the allocated power to a given channel. That's for one user in the channel. And then it will also calculate the guard band if things don't go in evenly. Stuff like that. Okay. It will tell you again, it repeats the bandwidth of the low end and the high end of the pass band in both the up and the downlink. Then it shows you a little pictogram of what the transponder looks like, and it gives you the ability to change all these parameters. So without belaboring the obvious, the one that you're going to be most interested in generally, here's, by the way, where you put the antenna pointing loss. And it's telling me that's coming from another data sheet too. That's over in the orbit. 4A in the orbit, it allows you to set the pointing loss. But the one you're going to care about is I have 2 antennas in my version of the system. And this one for the uplink is a lens-aided horn. It has a 20 that doesn't sound right. That's not right. It's not 27 degrees, is it? I think that the beam width is a little narrower than that. It's about Earth size, so it's about 20 degrees, and it has a gain of 21.8. I think I've got a bug there. Then you can set all of the usual things that you set for the noise that's established the system noise temperature for the system. And then over here on the transmit side, it's telling you, yeah, you picked up, before you picked up 10 watts. Then it allows you to have filter losses and line losses going to that. And it says your antenna gain is 17.2. This one has a 16-degree beam width. And I again have a pointing loss, which is given by one of the other spreadsheets. But I've got in there for the pointing loss allowed 1 dB. That gives me a net ERP of 26 dB. And it also calculates for those who care about things like this, the G over T.
Okay, so the pointing loss that you're talking about right there is entered in on 4A.
Let me see. Let's go to it. It's entered in on 4A cell K36.
Okay.
So 4A cell K36. Oh, it's taken from there, but if this is a double indirect, K36. Okay. And that's a complicated formula. It's saying, I got to remember my own. This is when you forget this, it's called bit rot. I know for a fact that, in fact, let's skip to the reality here.
It's got to be.
Antenna.
Yeah, it's got to come from somewhere. So we'll table it and
oh, it does. It does. I mean, I can cheat and go to the link itself. Let me do say the uplink, and you'll see that now this is, if nothing else, this should be fairly clear. This is the straightforward link itself. And if I come down here and I look, the ground station antenna pointing loss. So I got the ground station antenna pointing loss, but I also have the spacecraft pointing loss here. Spacecraft receiver pointing loss is here. K37. So it's telling me it's based on a calculation of some relative. I'll take an action item on this and explain to you how it's done that. It's flummoxing me right now. But okay. Let's go then back to here. So we're still calculating, but you see there's a lot more. No, okay, here it is. Here it is. Okay, so this is to properly define the antennas. Now you'll see we have our friend over here, this graphic again, because it's useful in setting these to see what it does. What we got is a frequency of thus and so. If the antenna, now this assumes guys, this is like what kind of, every antenna is going to have a different kind of equation to set its gain relative to, and its beam width relative to some parameter of the antenna. So just assume that this is a dish that I'm doing. It's the size of the dish that I would need with this aperture efficiency in order to produce this gain, and it has this beam width. So I was right on the beam width, okay? So an antenna that's 70 centimeters across at 10.5 gigahertz, and there's no parabola, there's no dish that's going to have an 80% aperture efficiency. A good high one would be 60 couple percent. So this is telling me this is a horn antenna. They have about 80% efficiency, and their aperture size isn't that different from. So this is a little bit of a fudge, but what you want to do is get the approximate antenna parameters between the antenna diameter. If you call it the equivalent of a dish, and the equivalent of a dish aperture efficiency, such that it comes out to meet the gain you know for your horn. So I know I have a horn with 17 dB of gain, and I bump this up until I get that gain. And then I say, well, it's a horn, not a dish, so it'll have an effective aperture efficiency of about 80%. So that's how that little tool works. And then you've got the same tool over here for the downlink, but of course the uplink, and it is occurring at 24 gigs, whereas the downlink is occurring over here at 10.5 gigs. So I've defined the antennas at this point. All right. Now, once I define them, I used another tool I developed a long time ago, and I say, okay, if I put that antenna in and I assume a sine squared theta over theta squared, which is what you would call the standard linear taper beam pattern for a dish antenna, and it works real well for a horn antenna too. Okay, so this is the angle from bore site over here in this column. And sorry, this is the angle from bore site in this column. And this is how much the beam rolls off. So this is the transmit. This is the transmit antenna beam. And what it's saying is, this is the roll off you get in dB for this particular angle. And you can see that the 3 dB beam width of this antenna is 13.54. Sorry, right. At 13.54 degrees total beam width, that's the half power beam width of this antenna. The antenna is rolled off by 3 dB. And I did it wrong. So let me try it one more time. The 13.54 degrees is from the bore site to the user location. And if that angle was 13.5 degrees, then the user would be rolled off on that antenna by 3 dB. The yellow line is actually
that would be the half beam width.
Yeah, it's the half beam width. That's right. It's the half. It's 1/2 the half power beam width. Oh, you see, it's there. Half power beam width divided by 2. So it's a half power beam width divided by 2. That's correct. So that's from the bore site to where the user might be located. Now, what this yellow line? This is a dynamic yellow line. This is using dynamic color control, and this is one of the new features I've been able to thread into this. For this link, the yellow line is the condition I'm meeting right now on the uplink. Okay, so at this time, this is the closest step that I'm achieving that I have in this step. So it's like a lookup. It isn't like a lookup table. It is a lookup table, and it's looked up and said, okay, you're at 7.98 degrees off. 7 point something degrees off, and this is the closest step, and the closest step is you are losing 1 dB in performance by being at that location. So you're inside the 3 dB beam width in transmit. However, over here in the receive side, we got a different situation. The half power beam width is 8 degrees, not 13.5. So it's a narrower antenna, and because it's a narrow antenna, what I'm achieving at 8.02 degrees is I'm achieving minus 3.03. So I'm already just slightly past the 3 dB roll-off point on the antenna. So as I change the link parameters, this yellow line dynamically moves up and down the page. It's telling you where the user is relative to the beam pattern. And as we move off, what we'll see as we go down here, look what happens if the beam pattern moves down to this area, which it very well will. I'll have a loss of infinity in dB.
Yeah. Wow.
I mean, 328 dB. So you're in the null. And so, dude, when you're in that null, you're not going to communicate. So that user, the ring all around for whatever elevation angle corresponds to that case, all the way around that ring, around the Earth, centered on the Earth center, there's not going to be any communications. So you have to sort of plan how that works in the way the system, where you are in the orbit and that kind of thing. There will be times where certain elevation angles will be in a null scenario. And there'll be some cases where it'll actually be able to perform and the link will close all the way out in the first side lobe. So
Yeah.
we can show some of the cases here, but you have to be aware of the fact that as you move away from apogee, if the beam can't adapt, then two things happen. One is the user will be, just on average, the user will be further off the beam bore site. And second of all, to the good side, the spacecraft will be closer to the Earth. So 1/r² is a lower path loss. So the link will just improve because the path loss decreased. So all that is figured out in this link model here.
Sounds great.
All right. Let's see. So that finishes with the spacecraft setup. Once you've done that, you've set up everything you can, and then you have to go to the users. And this is a lot more easy to figure out. If you play with this antenna here, and I say yes, then it will apply to the link equations, the link budget, this antenna, which has this gain and this beam width. If I select no here, it goes over and it will select the gain that you picked off that other choice on the link scenario planner. Let me do that real quick. There is up here at the top in the link scenario planner, you can check this box and uncheck these boxes. And then you'll be using that particular size antenna. This is a little bit complex, I agree. And you'll be controlling from this box here. But you see, it tells me I've not selected this. If I say no, then it says selected over here and not selected over here. If I say yes, it swaps them around. Selected, not selected. And if, again, I say no, no, and I go over to the link scenario planner, it will have changed the check boxes. These two become, no, that's interesting. Actually, I have to select no on the other one too. I have to select no on the other one too. And that's correct. So I have to go down here and say, nope, I'm not going to use this antenna. Now I'm operating in what you might call a duplex or diplexer mode, where I have the same antenna and it goes through to a diplexer, and you sort the transmit frequency and the receive frequency in the diplexer, and then you've got two coax cables, one going to the transmitter, one going to the receiver. So you can do either mode of performance here. You can have assume the user has two antennas or one antenna.
Yeah,
and that's how you.
That's pretty trick. And it is not. There could be a explanation here. Eventually.
Oh, there is. Yeah. There is. Let me see.
Is there like the notes on the page? Probably. Oh, there it is. Okay. Yeah. Thank you.
I try and put all these notes, and by the way, got to use the notes sometimes to figure out what's going on.
Yeah, yeah, that's pretty trick though. That's a tremendous amount of customization.
Here's the key one. Okay.
Yeah.
All right. So we got the user terminal sorted. So I can, what I did here, and now it's going back to not how you might use the spreadsheet, but how I am using the spreadsheet, is I put a 1 meter antenna in for transmit and receive, so I could play with these parameters while I was doing it. And I've got 60% aperture efficiency would be like an offset fed user antenna. So I assume that the user is using a microwave antenna he would have bought from his TV dish store, where he would get it and then he modifies the feed for his use.
Yeah.
But basically it's an offset fed antenna. So it's a little tricky to point for the average user, because of course it doesn't, the bore sight doesn't align with any physical feature on the dish. So it's hard as hell to make sure. You can't just go out with your eye and look at some reference point in the sky like a star and say, okay, I'm about right. you got to calibrate your system. But anyway, that's what's in here right now. Is the cheapest antenna I could get for a guy was a offset fed 1 meter dish, and it already has a beam width at our frequency of 0.87 degrees, which is damn narrow, and the same size antenna down here for the user on the downlink, which goes, Michelle, to the issue of, if I make it easier for receive than transmit, then he can slop around in 2 degrees.
Right.
Which is still pretty damn narrow. But he can slop around in 2 degrees rather than having to try and point to 0.87 degrees, which he needs for transmit.
Right.
Also, with transmit, he might be able, if you put the right feature, software feature in the spacecraft, he might be able to walk himself in if he gets feedback from the spacecraft saying, okay, your signal to noise ratio right now in the channel I'm receiving you on, using some GUI or something, is 6 dB. Oh no, now it's 8. Oh, it's 9. Okay, so he uses that to walk it in. He can walk in the transmit, whereas he needs the feedback he gets from his receiver to lock in the downlink beam.
Right.
And I assume there's going to be some kind of beacons here and there. We haven't talked about frequency referencing and all that, and that's a whole other chapter.
No,
in this thing.
it's a whole nother
Sure.
chapter, and we do have some work there, and some engineering and some ideas.
Yeah. So this is the area for the ground station where you put in whatever the LNA temperature is, noise figure. I don't have it. If you want, I can put in noise figure here, and I've got a little calculator. I can put a little calculator over here in the empty space, which allows you to go from noise figure to noise temperature and noise temperature, because hams are needing that all the time. So we can do that. But anyway, I've got it in proper engineering terms. So it's noise temperature. If you have a filter like a bandpass filter, typically the losses you want to get below a dB, and then whatever your transmission line lines, you want this all very close to the feed so you get this loss down. We all know that. But anyway, that's where you enter the parameters. Here's where the pointing loss of the ground station transmitter goes, and this gets fed into the link budget. And it's good to know at any given frequency roughly what the clear sky temperature is. Right. And that will be very much elevation angle dependent. So the way my link budget works, it assumes kind of a constant value for that. And even in a clear sky, actually, that does vary a little bit. So I call that a fudge factor. And what I have in there is my best guess at the fudge factor for that frequency and medium elevation angle.
Okay, so that's blue. That means that's the responsibility of the user of the
anything that's blue here is expected. You got to fill it in, and it will affect the link budget. Yeah.
Right.
Yeah.
Okay.
Okay. So then we go to the links proper, and this should look like a properly documented and annotated link budget. And the most important part of it, it looks pretty much regularly, like you'd expect to see. It's got all the pointing losses. It's properly computing, and a parameter you need to know is the axial ratio of the antennas you're using. So you'll see, where the hell is my axial ratio? Up here. Polarization loss. Okay, that's a big one. This, it's the main spreadsheet where you have to put the polarization loss. You guys, from some of my other, either get one of my other regular amateur radio spreadsheets, or you can implement the formula yourself. But you need to know the axial ratio of the transmit antenna, the axial ratio of the receive antenna, and then the angle between the two ellipses that are created by the two antennas when their axial ratios aren't perfect. And what this is telling me is that the axial ratio of the ground station antenna was 1 dB, the spacecraft antenna was 3 dB, and it's the worst case ellipse alignment. So the two ellipses thus created are in as cross pole as they can get. And under those conditions where I have a 1 in 3, the loss is minus 0.23. But that is a user entry. And I realized that I've got lots of spreadsheets that calculate that, but I didn't put it here. And if a user is going to use this, he'd benefit from having this be an equation. But for big guys like us using this, I'm assuming you would know how to either calculate that or estimate it for what your system is. But the polarization loss is, to a lot of people, is a big deal these days. And so that's where you play with it.
Okay.
And I wanted you to know that I do take into account in the, that's a downlink issue, so let's just stick with the uplinks. I don't deal with the linearity of the user on this link, Wally. The user's IMR, intermod ratio, or intermod losses is not really taken into account. I'm assuming that the ground station takes account of that in the transmit power here. So that's one higher level of sophistication I could add here that I haven't. However, I take care of that on the transmit side of the spacecraft.
Yeah, on the downlink side, does it make sense to stick a implementation loss catch-all?
It's a good idea to put that parameter in there if the implementation loss across the Mod Cod steps is fairly consistent, then it could be easily put as just before the bottom line of the link budget on the downlink. If it changes by Mod Cod step, then you have to put it into the Mod Cod table. We haven't got to that yet.
Okay.
All right. So anyway, so this is just everything standard, except what I'm doing here is I'm allowing you to pick between. I'm separately, once we get into the part where the rain losses occur, all the rain losses which are coming from the rain model are plugged in here, and these are the sums of them. And then from here on down the link budget, I compute the rain case, the rain on case, and the rain off case. And that's what you see, these two parallel numbers. You see them again here and here and here. So each time I apply some correction, there's two versions of the outcome, and they're carried. And then I copy. If I turn on the rain, it copies the worst value. If I turn the rain off, it takes the best value in each case. But the things I correct for here are the Met losses. Let's see. This is where I've computed the net effect. This is the number I would nominally use to do the Mod Cod table lookup. In other words, this is the end result of the link, except I haven't yet accounted for noise power in the receiver, and I haven't yet accounted for interference on the downlink. If I've got an interference environment I'm in, let's say I have something that's producing white noise that's going all over my receiver channel, I can put in the density of that noise here, and it computes the noise power of that, and then it figures out how much does that degrade the link. Okay. And yeah, for that case, but that's like, if you want to see it go worse, I go minus 200. Okay, and you see the link goes to crap because I put a very high, that's a fairly high interference density into that case, into that scenario. Then I end up with the classic signal to noise ratio. That's okay. It's the signal to noise ratio considering the noise also includes an interference, and that interference is defined by that blue box above. So if I turn off the interference so that it's really C over N plus I, but I is 0, then it becomes C over N. Anyway, that is the bottom line as far as putting it in terms of signal noise in a given bandwidth. There's the bandwidth. So I come up with the net effect. So that's in the transponder, and then this is in the user's receiver. And since they're identical, it doesn't change. And then I have a clear sky and a sometimes called unfaded and faded clear sky, and C over N0 plus I0. So I take that one into account. And that is actually the number here that I'm using in the ModCod lookup table. And I also calculate for the DVB-S2 table, if some people would like to know what the net EB over N0 parameter. It's another way of saying the signal to noise ratio, but it's the energy per bit to noise power density number. And so that's given here as well.
No, yeah.
Okay. So this part down here is where there is an implementation loss taken into consideration here. But since I've essentially disabled everything down here, because I'm going on to the ModCod tables, and I'm using a DVB-S2 demodulator. So fundamentally, I haven't really used this, but here's an example where I put the implementation loss into the link. So prior use of this spreadsheet, I was apparently using it for a BPSK link, and I had assumed that the DMAT had a half dB implementation loss. Okay. Now, if we go to the downlink, the only thing that might be different here that you haven't seen before is I calculate from the intermod value that's in here. I calculate the intermod power. So I say, okay, I got a 10-watt transmitter, but I'm producing, the intermod's 20 dB down, say, so I have an intermod of 0.1 dB, so that's 20 dB below 10 watts. So I'm losing to the intermod 0.1 of a dB. So the real power I'm actually transmitting on the link that's doing some good at the DMOD is 9.9 watts. So if I were, for instance, to go back and make the intermod value, which I think is all the way back here. Yeah, it's a spacecraft intermod, isn't it? Here's the spacecraft intermod. If I make it like a Class C amplifier or something where it's really crappy, you'll see now what happens. Now the downlink, which is still 10 watts, is losing 1 watt of power to the intermod, and it's only producing 9 watts of real power. So 9 watts now goes through the link all the way to the other end. Okay.
Yeah, but if the trade-off is efficiency, that may be a worthwhile way to go.
In that regard, you have to know what the efficiency hit is for a given intermod. So if I measure 15, and so it'll also, the way you will adjust that normally, and the big guys, when they do their transponders, they just have a variable attenuator, and they set an attenuator, and that will set the output back off. So if I back it off, say 3 dB, then I might have improved linearity. So I might get, say, 25 dB linearity. So I've got that trade-off. But I now only have 5 watts of power driving the link, but it's a much more linear link. And by the way, this, in the bargain, this number, if I went to a higher output back off, the efficiency might go down to like 20%. So that might be the circumstances for a fairly linear transponder with a pretty big back off. And I don't know if that's enough back off to get 25 dB. That might have to be 6 dB or something like that. But anyway, you'll pay for it with efficiency. Now you can go see how it affects the links, and you can see that my transponder power has gone up to 50 watts. So to get 10 watts out, I now need 50 watts of power in to make that system work. So I'll go back to what I had, which is it's a 10-watt transmitter. Its output back off was about 1.7 dB, I can't remember, 1.76. Transmitter DC to RF efficiency was 28%. I had about 20 dB interrupt. Okay. So with that discussion, this link looks a lot like the other one. Here's all the rain effects, and you can see the rain effects are much smaller because this is at 10 gigs and so on. And the same things apply here. And there's the net result in C over N plus I. And the numbers I really care about are these two numbers here, the C over N0 plus I0. That's what I'm using in the mod card tables. Now, this is the uplink mod card table. You'll notice there's a yellow line across here, and this means this is the mod card step that the link was able to achieve. So I look over here at the red number and I see, by the way, are you guys generally familiar with what these mod card tables look like? This is right out of the ETSI DVB-S2 standard.
Where you should say we are intimate with them.
Okay, cool. So this is what I've made adjustable here is I can see I've got a 5% Nyquist roll off. So this is a very, very sharp filter. And I might say for an amateur application, you might be able to use 10 or even 20% Nyquist roll off and nobody would care. And it would save probably power at the microprocessor that's making this filter exist. I assume it'd be a software-defined radio. And the sharper the filter, the more recursive steps that the filtering process takes within the software. And it usually chews up.
We use FFT, so it doesn't matter.
Okay, all right. But anyway, there's usually a trade space around using that parameter. But to be honest, if we're at 24 gigahertz, nobody's going to care how efficiently we use it. But if you want to, DVB-S2X is certainly supporting 5% Nyquist roll-off. Here we're using 5%, but I'm going to change that. I don't like that.
I think 15 or 20 is the limit on S2.
Yeah, I think 15 or 20. So I've over-specified that one. So you're right. And so, okay, so that now changes my, the allowable symbol rate. Because what I've actually said here is the hard channel limit. And then it says, well, how many, at that Nyquist roll-off, how many symbols can I actually cram into that 10 kilohertz channel? So now I can get 8.7 kilosymbols in that channel. Anyway, the mod card that was achieved was this particular step. And you'll see that what I did, and this is an artifact of the fact I was using these commercially, but we had a case where we had the uplink was using the S2 standard, and the downlink used the S2X standard, which it meant it used all of the S2 steps, but also all of the S2X ones. And I'll show you that on the downlink. And I figured here, it's also true that the uplink doesn't need that much partitioning on the part of the users. Whereas I'd like to get every bit out of the downlink I could, because the downlink is the hard one and the uplink was the easier one, even though it was at 24 gigahertz. So what you guys are going to tell me is I'm going to replace this table with a table that's going to have your mod card steps, which aren't going to look like this, but I need the data to create this table.
I think
Okay.
S2 is a good starting point for this.
Yeah, so S2 is a pretty good starting point because your list is going to be somewhere within this list.
Yes,
for sure. And maybe you'll be a little less efficient because maybe you don't have as good a coding or something, but that's whatever it is, it is.
This is pretty close to the best performance for APSK. We may not be able to do the linear codes, depending on the output stage.
But you can see that if I drop down to some of the other steps here.
Oh yeah, data rate, yeah.
Well, I'm actually talking about case where the case is where you are around the orbit. Actually, if I go down in altitude, I don't always improve the situation because of the beam roll off. So some users in some circumstances are going to get worse conditions, even though they're getting closer to the Earth, which is a sad outcome, but it's part of what I call the game, because there is a game here, and you just have to, as an amateur, you're not going to get everything perfect because you got it all for free. So you have to get what you get, and that's part of the fun of the whole thing. And that's kind of the way I look at these antenna roll-offs and things like that as well. Okay, so this is the whole downlink list, and you can see we can go from a mod cut step of 1 to 28. There happen to be 28 steps here, and that takes you all the way up to 32 APSK 9/10 and all the way down to QPSK 1/4. And if you're at QPSK 1/4, that should be about, you know, in your mental mind, you'd say, well, QPSK, I divide by 2, I multiply by 2, and by doing a quarter rate, I divide by 4. So that the total should be about 0.5, and you can see, give or take, bit sampling issues and overheads, it's 0.49 is the bit per symbol efficiency of that step. Whereas if I can go all the way up to 32 APSK, I can I'll go all the way up to 4.5 bits per symbol. I wanted to say that this is actually the extended steps. No, this is just the normal steps.
That's a standard table from DVB.
That's the standard table. And this other table is one that's also in the data standard, the ETSI standard, but it's a somewhat different table. And what we've done is we've automated that. So this has got all kind of conditional things in it, the way I'm using it. Okay, so that's it for that. Okay, so what happens is that there's a lookup table where it compares this value 45.81. We go back to the let's see, this is the downlink budget. Yeah, this is the uplink budget. Okay, so I go back to the uplink budget, and I see the number I got, the number I achieved with rain off was 45.89. So it takes the 45.89 and it looks, doing the lookup, it says the number which I exceeded but didn't get to the next step was 45.81. So I got 45.89 and I need 45.81. So I've got a little bit of margin, but that's the closest step. So it picks that step. So it's a lookup table. So the downlink one, now you'll see one thing. First of all, you see it's bigger, a lot bigger. Yeah, and this was what happens if you allow in your decoder, decoder demodulator. If you allow every single step in the S2X group and the old S2 group. So if you allow all those to occur, and we have a piece of equipment at work we're building which does that. So I put in all the ModCOD steps, and I highlighted the S2X ones just so you can know, well, did I land on one of the old steps or one of the new steps? Because we're actually comparing some old hardware to some new hardware, so that's why it's highlighted like this. But at least you can tell. And you can see on the downlink here, with what we've done, we've got now a allowable data rate of 2.25 megabits per second. Let me go back to the planner and see. So I changed something pretty big time. So now you can see, if I look at my measure, whatever I've done, I don't know why I've gotten that big. I'm getting 360 channels worth of use out. So I'm doing really well here. And I'm wondering, did the transmitter power is still 10 watts, 1.7, 20 dB. Did I make the user better? Let's see, I got something wrong here. I'm using that one and I want to use this one. So this wants to be a yes. Much antenna gain there. So now, I go to my downlink. Now I'm back where I thought I should be. So I had too much uplink antenna gain. And so now this is what I'd expect. I've got just round about a bit per hertz, and I'm getting just 100.9 megabits per second of performance out of that link. The next thing I want to show you is how the rain model is working here. So it actually uses the rain model twice, and this is what the rain model GUI thing that the ITU sends you looks like. You can see it's the ITU here because how they're spelling degrees in French. All the green parameters are plugged in. So I'm taking from that user selection, I'm plugging in his latitude, longitude, height, and whatever elevation angle is taken from the orbit data sheet. I've put in his downlink antenna size, which is also taken from tab 3, and the antenna efficiency, the frequency. This polarization parameter doesn't seem to work the way I thought it was. So I just put 45 in there and leave it alone. I think it's assuming a linear antenna and that it's a geo case, and so they're assuming that the polarizations are misaligned 45 degrees. I don't know. And then it wants the rain unavailability, and the one most everybody uses is the link rain availability, not the unavailability. So this is copied from the tab 3, the link scenario planner, and is put here. It then computes that number there, and then that's what the ITU rain model is actually doing. Then it says, okay, if you have that location, that frequency, that elevation angle, and that set of antenna parameters, here's what your weather looks like. And so it gives you for 99.5% of the time, if the link was only available a 0.5% of the time, it would be raining pretty hard. So the rain would be 35 millimeters of rain an hour. I don't know what that next parameter is. It tells you the mean height of the rain. It tells you how many along a 1 meter column. It's telling you what the weight of the rain would be in that column, and it's 0.35 of a kilogram. It's telling you surface water vapor densities and integrated water vapor, all these things that meteorologists would ask about. And then it's telling you also, well, okay, in a radio sense, the effective temperature of that whole environment you're in is 280 degrees Kelvin. And then the net effect of that on the link is it has 2 parameters for gaseous attenuation. The number you're supposed to use is this latter one. So that's really the effective gas loss. So at this frequency, which is 24.025 gigahertz in Boulder, Colorado, you can expect, without any rain or anything, just the atmosphere is going to kill 4.75 dB of your signal going in the uplink direction. And if you on top of that have rain and clouds, you get this additional part. And then there's something called scintillation. I think scintillation is a fudge factor, but okay, let's leave it in there. But the ITU says you can have scintillation on any frequency, and it's like noise that the atmosphere produces that mucks up your link, and it has certain noise statistical parameters, and I really have never very well understood it. but it's essentially atmospherically generated specific kind of noise. The way I like to think of it is, well, if I've got that much additional attenuation, then maybe I'm not uncertain about by about the same amount. So you can call it what you want, but it throws another dB into the mix. And then the one you're supposed to use is number 2 here. So we have, for Boulder, Colorado, on a clear day, we got, at this 10-degree elevation angle, we already have almost 12 dB of losses. So that's pretty bad. But if we go to clear sky conditions and we only count the gaseous attenuation and the scintillation, you see we get something like 5.86 dB. So with the rain off, we only have 5.8 dB, but with the rain on, it's nearly 12 dB of losses. And by the way, another useful number here is if I look up in the sky with those conditions, that's the temperature of the sky. Remember I said if at medium elevation angles you didn't have any effects of the atmosphere, the sky would look like about 35 Kelvin. What they're saying is, what the ITU says is, if you're looking at 10 degrees, that's the temperature you see. And so that number can then be used as the other temperature parameter you use in calculating the system noise temperature.
Well, that'll have a big effect on the downlink.
Yeah. Let's, for instance,
I mean the uplink.
Yeah, let's, for instance, go to the orbit. Okay, I've got an elevation angle here, and now let me make it be 45 degrees. All I'm changing for the link is just the guy's elevation angle. Now that's already fed into that link model back there for the uplink. Now it's, by going up to 45 degrees, the noise temperature has dropped down to 168, and the overall atmospheric losses plus scintillation has gone down to 4 dB. And without any rain or anything, it's dropped down to 1.37 dB. So now it's become a kind of a useful radio link. Okay, now it works fine. But it's telling you that down at 10 degrees, that user is gonna struggle. And that's something you got to figure out when you figure out how you're going to set up the transponder to make it easier or harder for that user to go to access the transponder. So by setting up the transponder conditions, you can actually set what elevation angle practically the average user will be able to get down to before he'll lose the link. And of course, if he's in a wetter location, he's going to have a higher elevation angle before he can play. Whereas if he gets, a higher elevation angle and he's in a drier place, he's going to do better. So all those things one would in principle need to parameterize in order to be able to do the transponder setup the way you'd really like to have it.
All right, sounds good.
All right, and the last thing is a summary thing that shows you the results, and then that's just, there's no changes in that, but it breaks things up by what the user's parameters are on the uplink, on the downlink, and then what the spacecraft parameters are. So that's all summarized there. And then if I can get this last one, and then here's a pretty picture that shows what everything looks like as you go through the system from one end to the other. And the last one doesn't count. So
great stuff.
I think you can see where the trade spaces are here. And I see some trade spaces very clearly, of course, for due to rain, and whether you have the rain on or off. And it's a very strong function of regardless of where the user is located, his average elevation angle. And I think you can see that the overall system performance, how many channels of users you can support where each channel in my definition was a voice grade channel. I use that 6.25 parameter, but that can be a different parameter, of course. But in order to get 100 channels for the users over the whole range of different parameters, which you can change here.
Well, it's really hard. We'll have a baseline everybody can do, probably QPSK 1/4, maybe
Sure.
a half. And that will be a low power, 2400 bit per second. Everybody has that capability. But they may not be able to receive anything that's above QPSK 1/4, which is fine.
Yeah, but by having a tool like this, you can play with all those parameters and you can make certain sort of statistical judgments about the user community, like
Exactly, yeah.
average antenna size, average ERP of the user, how big. I assumed here that RF power was pretty hard, but you know what? Because of gallium nitride, these devices are getting better all the time. So
it's getting
it might be
easier and easier.
Yeah, it changes. It changes almost monthly.
To do 24 gigahertz on the ground is easy.
Yeah, well, so whatever you want to assume there, I've assumed that we use the old number we used to use maybe 5 years ago, which was it's pretty hard, so we don't make the user generate more than 1 watt of RF, but he also wants a small antenna. I'd like to give him a 0.5 meter dish, but instead I gave him a 1 meter dish to make the uplink ERP look better. So those are the kind of trades you can make. But do realize that where 24 gigs comes into the picture, you've got to be ever mindful of the mean rainfall. And somebody who lives in Mississippi or Louisiana isn't going to like this system as much as somebody in Kansas or
Arizona.
Colorado or Arizona. They're just not going to like it because they're going to eat 7 or 8 dB all the time due to that water vapor absorption.
Well, I think that's something that will be appreciated both through the modeling and through actual experience and usage. It's
right.
Remarkable.
Part of the fun here is to let people play with the systems they synthesize and come up with. And you know how our community works so great to say, look, you go to a conference, look what I did. And then everybody else next year will have what that guy had, but that guy's moved on to something else. So
exactly.
Yeah. So it is interesting that this should stimulate a lot of development work, just because it's not a piece of cake.
Yeah, I can't wait. Thank you. This is fantastic.
Okay, so if you guys want to give me what the user uplink usually looks like, or just maybe send me an email and say, well, this part of your link model isn't applicable because we do things this way or that way.
Yeah,
because obviously I'm doing it from a system I designed from inside my cranium here.
Yeah, I'll put some details together for you so you can see what our architecture really looks like. You're probably most familiar with CC, so you can use that as a baseline. Anything will be close to that.
Oh, CCSDS.
Yes, yeah.
Oh, okay. And would that be there? Which standard there? Do you know? Do you remember the number or the title?
I think it's the blue book. But I'll dig it out.
They're all blue books.
We'll track it down.
Sure. But yeah, then if it's a CCSDS, then all the detailed numbers are there, and I can plug those in.
Yeah, then you'll have a good idea what the numbers are.
Yeah. So in terms of what you guys are assuming for the users, that's maybe the place where I'm the most out of date because I actually haven't pressed a CW key in 20 years.
We're, we're assuming that the user can operate this
Yep.
like it's a walkie-talkie.
Okay, like it's a walkie-talkie, but not in terms of the antenna, of course.
Right.
No,
No, and
Yeah, okay.
we
the end user.
we could send some descriptions, you know, the sort of the use cases that we assume, some the feedback that we've received, and what we think will be innovative, fun, and easy to use.
Yep. Well, if you guys could somehow figure out how to get this link model to work, and Michelle, you're now familiar with the issue of trying to get this to recognize the ITU ring model to recognize 32-bit numbers instead of 64-bit numbers in the thing. And I'm really frustrated with the ITU about this whole thing. But anyway, if we could get the rain model working, then you guys too can play with this and change parameters and do what you want. And I think it's pretty educational to, another thing to play with is what is the optimum antenna beam width for this joint. You've got a dual feed antenna or dual frequency antenna. So what are the optimum beam widths there for that antenna? It's a big trade factor there, I think.
Yeah, it is. That's a very good point.
Because as you see, as you get closer to the Earth, the link doesn't necessarily get better, but you've got two competing factors. The beam is, you're rolling off more on the beam, but you're getting closer to the Earth, so the signal is getting stronger just because of 1/r². So you got those two competing factors, and it's not entirely intuitively obvious what the absolute best gain of this antenna would be.
Right, and that's that's very exciting. I think this is great.
Yeah, and I'd also like to see this with the orbital parameters for a near geo. That'd be very.
Well, you can do that now. This is for geo. What you're looking at is geo because I'm at apogee, and apogee is geo.
Right.
Yeah.
So
all you need to do is
circularize
figure out what the user's elevation angle would be to that geostation, you know, that longitude, and then from that plug it in and you'll have the link for that individual.
Right.
Okay.
I've got another spreadsheet that does that kind of math if you want that one.
Sure.
I've got a geo link model too, but it's where you can put in the Latin one of the user A, user B, and then the satellite station, which is its longitude. And then it tells you azimuth, elevation, and slant range.
Okay.
Yeah, it's mostly the uplink because everybody has to have a downlink or they cannot do anything.
Yeah.
If they're not receiving the downlink, they're off the air.
And one thing you might want to do is consider beacons here. And I think maybe because the word beacon has been so confused by the CubeSat community, I want to define what I mean by beacon. But a subcarrier that's put with the downlink that somebody can use for tuning purposes. And it would be really cool if whatever you decide for the uplink, whatever digital channel you decide, could have a mode where that, you know, like there's an alternating 1-0 pattern the user sends in that mode, and what he gets back is his resultant signal to noise ratio, C/N0.
Right.
Yeah, we already.
So he
have
knows
modes
whether he's tuned his antenna, he's turning his antenna in the right direction.
Yeah, no, we have modes where they can monitor all the signal parameters. That's done routinely because when it starts raining, they're going to have to see that their power is not enough, and they're going to have to adjust the power dynamically. That's going to happen all automatically.
Yeah. Okay.
Yeah. There's plenty of room for really truly fun and different things. You know, like the.
Yeah. If you guys have a paper on the you know, sort of the goals of how the transponder would operate, that could be really interesting.
Yes.
Yeah, we have some stuff that's published that walks through the basic concepts of how it operates, and someone working on more detailed authentication authorization, the loop, the acquisition loop. And so we do have some written work, and Wally is going to really take that base that we have that's currently published, and really bring it up to more complete level here in the very near future. So I can get you some links to the stuff that's in our repository now, which should be a quick read. Let you see where we're at, and then Wally will have some more detailed work coming out soon.
Okay, good. How close am I with respect to the size of the antennas for the user and the power level of that user at 24 gigs?
Yeah, I think the antenna size looks reasonable to me. We do have a supply of some really nice dishes that we're collecting and moving from one location to a storage location in Alabama. So, since we have this supply of dishes, that may be a good one to start with. I think we have 30. So our plan was to make a
how big
bunch
are those?
I think these are a meter. They're a meter dish. They're nice.
Okay.
I'll send a data sheet to you.
A cool thing to do would be if you could measure the beam width of that antenna too at
Exactly.
24.002
Okay.
or something.
Yeah, we will. We're now at the point where we're able to do a little more traveling, and for people to be able to move around and move this particular set of materials. And we have some larger dishes too in the collection. I think these are 6 foot, so they're pretty large, different.
Yeah, 2 meters.
Yeah.
2-ish meters.
Yes. So we do have some of those. And that's it for dishes. But I think the dish size assumptions are good. And I don't know, Wally, what do you think about the power?
It feels right for 1 to 2 megabit downlink. Seems
Yeah.
a good
Okay.
match.
Yeah. Now you guys were saying you were thinking of much higher data rates on the downlink, but you can see you're very much link limited to get too much more. I mean, we're already using the best modulation coding scheme known to man, so that's not an area you can improve in.
Well, no,
So,
you can't. You're at basically at Nyquist already. So
yeah, you are. Shannon's starting to speak to you real loud. So would to get that, would you up the power to say a different class of spacecraft? So you're using more like 100 watts to generate maybe 20, 25 watts?
yeah, I think we probably our baseline power level, I think in GEO needs to be about 100 watts.
Okay, well, that's either a 16U, a 12 or 16U spacecraft, and the launch cost of that's going to be the better part of
it's a very clever 6U or a probably ordinary 12U.
Yeah, there's a group in Boulder actually that I have worked with who have got this really cool fold up thing, and I've tried putting those, in a cartoon sense, in a CAD sense, into a side of a 6U, and I think I can get about 70, maybe somewhere between 50 and 70 watts. But
No, that's not bad.
gosh, 100, that would be good if you could do that.
Yeah, that's the only way we're going to get our power up to our downlinks up much higher than 1 to 2, because they're going to be link limited.
Right.
Yeah, well, and that's kind of what I'm predicting. And I think, again, my metric was if you can't get 100 channels, you can't really call. I think you'd need too many spacecraft otherwise, and therefore it wouldn't be cost effective. You got to work for something like 100 channels equivalent user. So 1 channel used by 2 users is 200 users per spacecraft. if you can't get that kind of number on an international system, I don't think it's really very international anymore.
No, our baseline is 96 channels in the
Okay, we're talking,
lowest performance mode.
right. Okay. And, you know,
2400 bit per second. But
okay,
within
so you're
that,
talking,
those channels can be larger if the uplinks can be closed.
Right.
mhm. Well, I mean, you know, what you'll notice, I'm sure, before this is over, is there'll be portions of the orbit which favor good and bad conditions, and it's not necessarily driven by the height, the distance from apogee either. It's because of the you know, the first nulls of the antennas. You'll probably find that there are spots where, on average, the users will do better than on other spots on the orbit, and so you can try and adjust what the users are doing at those times based on that. In other words, there's lots of games to be played here, and while those games couldn't be played if you were professionally doing this, where you have to assume a comlink is presented 100% of the time with 99.99% reliability, we don't have to assume that.
No, but it's still our target.
Well, it'd be nice. And I think if you could do something that's quasi-geo, you could get there.
Yeah.
And I think you can get arbitrarily close with an NGSO. You just have these antenna problems
Right.
that can't be really avoided.
All right. Let's go ahead and call it an evening, and meet again really soon. I have some
Okay.
action items written down here, and I'm sure that we will have plenty more to talk about and catch up on. This has been absolutely fantastic, and what I'll do is I will edit up the video. Yeah, this is exciting. So I have plenty to do on the document with the documents you sent me, the action items from tonight. And is there anything else that I can do to help make this great?
No, I don't think so on this. But let me know if you want me to do a final edit on the white paper for the FCC thing. I'll do that whenever you say it's ready.
I'll hand it off to you for a final pass, just to make sure it's still coherent and has the right flow, didn't duplicate anything or leave anything out. And I'll try to get that finished as quickly as I can.
Okay. All right. So I think I've given you everything I owe.
I think you have, and more.
And yeah, thank you. And so let me know.
Okay. Yeah, I will. Thank you so much. I owe you drinks and dinner and all sorts of wonderful things when we can meet back in person.
Whenever, if and when we can ever get together.
I have faith.
I hope this dreaded disease gets over soon and everybody gets vaccinated.
All right. Yeah, we'll meet again soon.
Okay.
Sounds
Be good, guys.
All right. You
If
bet.
you can't be good, be careful.
You got it.
Bye.